All right, so we're going to do even more related rates, and they're going to get a little bit tricky. So sometimes related rates problems can get very tricky. When you first learned related rates, we did not plug in any numbers before taking the derivative. So I was a little bit lax on that last time. I let you plug in a couple things, right, if we noticed it was constant. Okay, so that's going to be the big thing in this lesson. If you have constants, plug them in. You did have the following one, or a similar one in your homework. But the weird thing about this first question is the degrees per minute versus radians per minute. So we're going to go over this question again because it's been a few days since we've done it, and make sure you guys understand. So it says two sides of a triangle have lengths of 12 meters and 15 meters. The angle between them is increasing at a rate of 2 degrees per minute. Okay, so we have 12 and we have 15, and we have some kind of angle between them. So theta. And then this side is actually changing depending on how wide those are opening. So d theta over dt is 2 degrees per minute. So how fast is the area of the triangle increasing when the angle between the sides is 60 degrees? So we can't plug in 60 degrees for theta because we're saying at that instant in time, how fast is that angle changing? Okay, so it's changing throughout the problem. So we have to plug it in after we take the derivative. So we're using a equals 1/2 ab sine theta. But we know we can plug in 12 and 15 for our side lengths because those are constant lengths. But we can't plug in anything in for theta because it's changing. So when we do that, we get 180 times 1/2, so 90 sine theta. And now we've simplified enough so that we can take the derivative. So when I take the derivative, I get dA over dt equals 90 cosine of theta d theta over dt. Okay, and I can plug things in. But you should always, whenever you have something that involves d theta over dt, an angle, you should be thinking about what your units are. So you should be very careful as you're going through. So as we plugged in the 12 and the 15, these were in meters, right? We had 12 meters and 15 meters. Okay, and we want dA over dt, we want meters squared per minute, right? The change in the area, meters squared per time, minute. Okay, and when I plug in the 60 for the theta, that's okay, because cosine of 60 is just a number, it's just 1/2. But if I plug in the 2 degrees per minute, that's not good, okay? Because if I'm plugging in 2 degrees per minute, and I'll write it here, but don't write it anything. My units would now be meters squared from the 90 degrees per minute, which is very strange to have meters squared degrees per minute. Okay, we don't want the degrees in there. So what we have to do is we have to change this 2 degrees per minute into radians. Okay, so when I have 2 degrees per minute, I put the degrees on the bottom, and let me do times there. Just like your, science conversions. We put degrees on the bottom, so I have 180 degrees pi radians. And I multiply it out. So I end up getting 2 over 180 makes 1 over 90. So I have pi over 90 radians per minute. But the nice thing about this is that radians is totally a made-up thing. Radians is nothing. So in science classes and math classes and so on, radians is what we call the non-measure. There's nothing there. Okay, it's a word that we've made up to indicate kind of like a length almost. So we don't have anything when we write radians. It's just kind of blank. So what we really have is pi over 90 times 1 over minute. Okay, and that's what we want. We want pi over 90. So then our units in the end become meters squared per minute. Do you guys understand that? Okay, is it better seeing it the second time? I know the first time you guys saw it, you're like, what? All right, so we're going to reduce out. So 90 and 90 reduce out. Cosine of 60 is 1/2. So our answer becomes pi over 2 meters squared per minute. All right, so that's the first kind of strange thing when we have, something. It's usually when it's d theta over dt. That's when you have that issue, right? D theta over dt. But if you're just plugging things in, like cosine of 60 degrees is the same as cosine of pi over 3, It's still just a number. It doesn't matter if it was radians or degrees. Okay, so let's try the next one. So it says a balloon rises at a rate of 3 meters per second from a point on the ground, 30 meters. From an observer. Find the rate of change of the angle of elevation. So our angle is changing. It's getting bigger as the balloon goes up. This distance here is constant. That is definitely 30, right? You're 30 meters away, the horizontal distance. But our vertical distance is changing. So I'll call that h, or you call it y, or whatever. So that is definitely changing. Okay, so the problem that we have is we know that dh over dt is gaining 3 meters every single second. What we want to find is d theta over dt. So it says find the rate of change of the angle when h is equal to 30 meters. Okay, that's our task. Okay. So we want to come up with some kind of equation that relates theta, h, and 30. So does anybody know what kind of equation we use? Yeah. Yep, tangent of theta equals h over, and you can use x, or you can actually plug in the 30 because that one is a constant. And you can multiply the 30 over if you want to, or you can think of it as 1 over 30h, so you don't have to use the product rule, right? Make things easy on yourself. And then we take the derivative. So our derivative is going to be secant squared theta, d theta over dt, equals 1 over 30 dh over dt. So we don't have theta. We don't know what the angle is. But if we draw the picture again, and we say, oh, it's at that point of time when your height is 30, then you can tell what theta has to be. What does it have to be? 45 degrees, or pi over 4, right? So in this case, it doesn't matter which one you use, because if you have secant squared of 45 degrees, it's the same as secant squared of pi over 4, right? It doesn't matter because you're just getting like a fraction out, a trig ratio. So secant is going to be 1 over cosine. So I'm going to have 1 over cosine of 45 degrees, or pi over 4, and I'm going to square it. And then d theta over dt is what we're trying to find. And we have 1 over 30, and then dh over dt is 3. So do you guys know 1 over cosine of 45 degrees? Yeah, it's 2 over root 2, like you're flipping it, right? And then you square it. So what happens when you square it? Yeah, you get 2, because you get 4 over 2, which is 2. Okay, so we get 2 d theta over dt equals, this side becomes 1 over 10 as I reduce. So d theta over dt equals 1 over 20, but then we're kind of stuck again. It's like, wait, what units did we have? Because in this case, I used degrees. Does that mean I end up with degrees? Nope, it doesn't, because I could have used degrees or radians there. Okay, so think about your units through the problem. Okay, the dh over dt, the dt part was in minutes, right? Minutes, no, seconds. Okay, so we definitely have something over seconds. But what do you think the d theta over dt is? What do you think the theta is in? It's radians. So it's radians per second, because we never along the way had anything that said degrees, right? I didn't multiply anything with degrees in or anything. I did have the 45 degrees, but that ends up just being a number. Like cosine of 45 degrees is just a number. It's called a trig ratio. Okay, so your answer should be in radians per second. So the same thing applies to these types of problems, where if you're finding d theta over dt in the end, it's radians over seconds, or radians per minute, or whatever. Okay, so you're going to end up with radians. So it's a little tricky. All right, so number 3. So a construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of the plank. The worker pulls the rope at a rate of 0.15 meters per second. How fast is the end of the plank sliding along the ground when it is 2.5 meters from the wall of the building? So let's write what we know. Okay, so we kind of have this drawing. Whoops, that's straight. Plank. Draw it again. So this drawing, And I'm going to call it x, y, and z. Okay, so let's think about x, y, and z. Is x getting bigger or smaller? Smaller. Is y getting bigger or smaller? Bigger, right? So x is going to be a negative number. Y is going to be a positive number. What about z? It's constant. So what could I actually plug in for z? 5. Yep, so before I even begin, I could erase that z and I could just say, oh, well, that's a 5-meter plank. So I'm going to put a 5 there. Okay, and I realize that the guy's above and he's pulling a plank, but it's still just affecting that distance y, right? So we can still draw it like a triangle. So we're going to have x squared plus y squared equals 5 squared. So when we take the derivative, we get 2x dx over dt plus 2y dy over dt equals 0. Right, the derivative of 25 is 0. And like all of these problems, you can divide by 2 to make it a little bit easier. So the things that we knew that z was 5. It says the worker pulls the rope at a rate of 0.15 meters per second. That's our dy over dt. So dy over dt equals 0.15. And it's positive, it's increasing. Dx over dt is what we're finding. So we're finding dx over dt when x equals 2.5. Okay, so we know some of this stuff. We know x is 2.5. We're finding the dx over dt, so it's okay, we don't know that one. The y, we don't know. But we do know dy over dt is 0.15. So we still need to find y. So we go back to that little triangle that we drew, and we say, okay, well, x at this point in time is 2.5. So we have 2.5 squared plus y squared equals 5 squared. And we can find what y is. So when I do the Pythagorean theorem and solve for y, oops, that's a weird y. Y ends up being 4.330. So I'm going to plug that in. So 4.330 there. But I'm going to keep that number in my calculator because I've rounded. So I keep my 4.330127019, that number in my calculator. I multiply by 0.15. I subtract it over, so I do negative answer, and divide by 2.5. So we end up getting dx over dt equals negative 0.260 meters per second. That's our answer. Okay, does that make sense? Usually people like the Pythagorean theorem ones, those are like the easy ones for students. All right, number 4. So gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms in a pile in the shape of a cone whose base diameter, its diameter, is the same as its height. So the diameter is always equal to the height. Okay, so as it's falling, it's growing vertically, but it's also growing horizontally. Really, that doesn't often happen. So this grain is this gravel is very special. All right, so it says, how fast is the height of the pile increasing when the pile is 10 feet high? Okay, so I made you guys some little formula sheets after I passed them out at the beginning. So 5th period requested that I write down some common related rates formulas, and I did that. But you don't get to use it for your test. You just get to use it for your homework. So you're still going to memorize it. But at least you know what you need to memorize. So one of the formulas that's on there is the volume of a cone. So the volume of anything that has one base ends up being 1/3 area of the base times the height. So if we have a cone, it has a circular base. So the area of a circle, right, the area of the base is going to be pi r squared. So you're going to have 1/3 pi r squared h. Now, on any related rates problem, when you have a cone, you should always think, can I set up some kind of proportion that has similar triangles? Can I remove one of these variables? Can I make this easier on myself? Because right now, if I was going to do this problem without replacing anything, you'd have to do the product rule. Okay, and it gets kind of messy. It's really long. So we want to avoid that if possible. Okay, and in this case we can because we were told that our diameter is always equal to the height. In other words, 2 times the radius is always equal to height. So as I go through the problem and decide which one I want, R or H, it says how fast is the height of the pile increasing when the pile is 10 feet high. So we want everything to be in terms of H. So we want to replace that R with H over 2. Okay, that's what it's always equal to in this pile. So I have 1/3 pi, R in this case is H over 2 times H. And the whole point of doing this is so we can avoid the product rule. So you always want to simplify as much as possible. So as I simplify, I get 1/3 pi. I have H squared over 4 times H. So I get pi over 12 H cubed. So that's very easy to take the derivative of then. So when I take the derivative, I get dv over dt equals, you can pull the pi over 12 to the front and then just take the derivative of h cubed. You get 3h squared dh over dt. Or you could have done it all together and had pi over 4h squared dh over dt. Doesn't matter. Right, the 3 and the 12 reduce. So now we plug in what we know. We know that the pile is 10 feet high, so h is 10. We want to find dh over dt. What was dv over dt? Yeah, the 30 cubic feet per minute. And it's growing, right? So we have 30 equals pi over 4, 10 squared dh over dt. So you can find it all as a decimal if you want, or you can reduce it down to a fraction. It doesn't matter. Pi over 4 times 100 is going to be 25 pi. And then if I divide that over, I get 30 over 25 pi is my dh over dt, which reduce, oh, yep, I wrote it wrong, didn't I? Thank you. That would have caused some problems, and I always warn you that people do that all the time. All right, and then we reduce down. So 30 over 25 makes 6 over 5, right? So it's like that, and that's where I was going to warn you not to do the pi on the top as you put it in your calculator. So if you want to find a decimal answer, make sure that you put in your calculator parentheses around that. Okay? So as we do that, we get 0.382, and our units are feet per minute. Okay. So be careful. Sometimes in these problems, I like to kind of throw some curveballs at you. Sometimes I put things in inches and feet. You know, you want to make it all in feet or all in inches or whatever. Okay, so look for things like that. But yeah, usually in cone problems, you can use similar triangles in some way to make it so you only have one variable. Well, two really. V equals something with one variable before you take the derivative. Okay. The fun one. All right, so number 5. So it says the cross-section of a 5-meter trough is an isosceles trapezoid with a 2-meter lower base, a 3-meter upper base, and an altitude of 2 meters. Usually I do a triangular trough before I do this. A triangular trough is one that looks like a triangle on the end, right? And with triangular troughs, so you don't have to draw this, I'll just show you. With triangular troughs, you end up having, like, the height of the water is in the same proportion as the height. So let's say this was 15 and this was h, and then this distance was 10. Well, this is going to be like a base, I guess. Right, and then you can set up your similar triangles. Do you guys understand that? Okay, but with trapezoids, it's a little bit harder. Actually, a lot harder. So they're pretty difficult. Okay, and the reason it's harder is because you can't actually use similar trapezoids in this problem. Okay, what a similar trapezoid is a 4-sided figure, right? If that's a trapezoid, right? Quadrilateral trapezoid. But all 4 of those sides are in the same proportion. So, like, here's an example of a similar trapezoid. If I have 4, 2, and 3 here, but then I had 2, 1, and 1.5. Do you guys see how those would be similar? They're all in the proportion like 2 to 1. Okay, but the problem with this is if I look at the whole big trapezoid here, and then this little trapezoid here, why can they not possibly be similar?
If that's drawn to scale, it's because it's not.
Yeah, that base is the same, exactly. So they can't be similar because one's smaller, but it has the same measurement along the bottom. Does that make sense? So we can't actually use similar trapezoids to solve this problem, but you can use similar triangles, and that's where it's weird. It's like, wait, how do I use a triangle to solve a trapezoid problem? All right, so here's what we're going to do. So we're going to label everything first. So it says the cross section of a 5-meter trough. So when it says 5 meters, it's talking about 5 meters long. So this is 5. With a 2-meter lower base, a 3-meter upper base, and an altitude of 2 meters. So we have all the labels there. We want to decide what one's constant. Now, when I'm talking about constant, I'm saying when it's totally full, like if it's totally full with water, the height of the water is 2, the upper base is 3, the lower base is 2, the length of the trough is 5, right? If it's totally full. But now as the water starts to drain out, which of those numbers is the same? The 5 is the same, right? That's a constant. And the lower base, that's a constant. But the other 2 and the 3 are not constant, because you guys see as the water is dripping down, it's getting small. Okay, so this is where I told you I went to an AP conference one time, and there was a teacher there that was like, oh, I never let my students plug in any numbers because they always mess it up. So I just make them leave all the variables in until after they take the derivative. Okay, well, if you have a trapezoidal trough, right, its volume is going to be the area of the base times the, I'll call it length in this case. That's the length. Which the area of the base is a trapezoid. It's 1/2 h times b1 plus b2 times L. So if she doesn't let people plug things in, she has h, b1, b2, L, and b. That's insane. Like taking the derivative of that is terrible. Who would want to do that? So that's why I get really upset when I go to those AP conferences and they're like, oh, I don't teach my students to plug in the constants. I do. I show you the right way, right? I show you the easy way of doing it. You just have to know that you can only do it for constants, right? So we're going to plug in the things that we know. So we know that H is changing. B1, it doesn't matter which one you call B1 and B2. We'll call this B1 and B2. B1 is changing. B2 is constant. L is constant. So we can plug those in. But it's still messy. We still have B1 and H. So you can go with it. You could do the product rule at this point. But at some point along the way, you're going to have to draw a certain diagram that you guys are going to hate. It's not easy. You can draw this picture. So you might as well do it before you take the derivative. Okay, so here's what the picture is going to be. So you might want to draw it kind of big. It's hard to see. So the water is leaking out of this trough, right? And the height, so this distance from here to here, was 2. But that's not the height of the water, right? The height of the water is here, h. And we know that the lower base was 2, and the upper base is 3. But that's not the height of the water. That's the height of the whole trough. Or that's the, not height, but the base length for the trough. And I told you that we can't use similar trapezoids, but we can use similar triangles. Do you guys see where we have the similar triangle? They're on the sides. There's 2 of them. Okay, so we're going to have, I'm going to call this x here and x here. And that's h as well. So I start to set it up and I'm like, okay, well 2 is in the same location as the height, 2 over h, equals something over x. Who can tell me what number goes right here? Ah, good job. How'd you get it? Okay, so explain that a little bit better than 3 minus 2 divided by 2.
So you take the length of the whole thing minus the bottom part.
So this whole thing is 3. This whole thing is 2. So he's saying if he subtracts the 3, if he subtracts 2 from it, he has 1 left. Well, 1 is going to be divided into those 2 pieces, right? So do you guys see why it's 0.5? That's exactly what it is. Good job. So we have 0.5 up there. Okay, which allows you to multiply. You could say 2x equals 0.5h. So when we go back to our problem, it's like, wait, but we have b1 and we have h. But what was b1? b1 was, really b1 is down here on the bottom. b1 is there. b1 is really made up of x here and here. Someone whose phone was buzzing, it's mine, sorry. I don't know how to turn it off. I just made it so it vibrates now when it's on silent. It throws me off. All right. So what do we do? So B1 is going to be what total?
Like B1 is the
Yeah, B1, what can I replace it with? Yeah. Do you guys see how I got that? Yeah. So this total distance here is 2x plus 2. So I'm going to have 1/2 h 2x plus 2 times 5. Okay, but what if I don't want x's? What if I want it all to be in terms of h? Yeah, you guys are good. Yep, 2x was equal to 0.5h. So we get that. Okay, so now everything's in terms of h, and now it's going to be very easy from here on. Okay, but that picture is not nice, is it? You guys, I'm sure you don't like the picture, but once you do one on the homework by yourself, like using that as a guide, you'll be like, oh, I totally get this. But it takes a second to kind of digest. All right, so now we're going to multiply this in. So I have the 1/2 h, but I also have the 5 on the end. So I'm going to write this as 5 over 2h, and then get rid of this 5 before I've distributed. So I'm going to have 5 over 2h times 0.5h. So 5 over 2 times 1/2 is going to be 5 over 4h squared. And 5 over 2 times 4 is going to be 10h. Okay. We know how to take the derivative of that.
Would you stop down on the way to morning meeting?
Oh, yeah, sure. Oh, no problem. So I have dv over dt equals 5 over 4 times 2. So 5 over 2h dh over dt plus 10 dh over dt. And I plug in. All right, now we just plug everything in. So it says, how fast is the water level rising when the water is 1 meter deep? Okay, so I want, what did I have? The dv over dt was 1 cubic meter per minute. So I have 1 equals 5 over 2 times 1. I want to find dh over dt plus 10 dh over dt. So I can add those together. I have 5 over 2 plus 10 gives me like 12.5 dh over dt. Or I could have pulled out the dh over dt if you wanted as well. So I divide it out. So 1 divided by 12.5 is 0.08. So 0.08 meters per minute equals dh over dt. That's our answer. That is as hard as I get, guys. It's like the hardest related rates problem you can possibly have. Maybe. Usually they don't get that hard, but you might have like a cone problem or something, right? But college classes might. All right, let's see, how much do we have left? We can do this one. So water is leaking out of an inverted conical tank at a rate of 6,000 centimeters cubed per minute. At the same time, the water is being pumped into the conical tank at a constant rate. The tank, so it's an inverted cone, right? The tank has a height of 600 centimeters. And the diameter, oh, I always draw these wrong, is also 600 centimeters. I should have looked first. If the water level is rising at a rate of 29 centimeters per minute, so dH over dt equals 29, when the height of the water is 150 centimeters, find the rate at which the water is being pumped into the tank, so the dV over t. So when h equals 150 centimeters, find dV over dt. Well, yeah, it's really the rate at which the water is being pumped into the tank. It's also being pumped out of the tank, right? So our dV over dt involves the rate in and then minus the rate out. Or if your rate out is negative, I guess plus the rate out. What should I say? I'll say plus rate out, but I'll say it's negative. Okay. kind of tricky. So we're not going to worry about this 6,000 till the very end, because that's how much it's leaking out right now. But I want to find the total change in the volume first, okay? So I'm going to have V equals 1/3 area of the base pi r squared times H. So as the water is draining, you guys do have similar triangles. So you have the radius of the water and the height of the water is in the proportion 300 to 600, right? So radius over height equals 300 over 600. In other words, radius over height equals 1/2. So 2r equals h. So we want the height, right? The water level is rising at a rate of 29 centimeters per minute when the height is 150. Sometimes you have both things, and then you kind of have to play with it like after you're plugging things in. Remember how you can always take the derivative here and say 2 dr over dt equals 2 dh over dt if you ever, or equals, not 2, equals dh over dt. So you could always do that if you weren't given like all the h's or all the r's. So we have pi, r is h over 2. So we end up getting 1/3 pi h squared over 4 times h. So pi over 12 h cubed. Cubed is looking weird. So now we can take the derivative. So I get dv over dt equals pi over, it will be 4 h squared dh over dt. And I plug everything in. So I know h is 150 centimeters. dh over dt is 29. dv over dt is what I'm trying to find. I'm just going to find it all as a decimal. Well, it would be 163,125 pi. But as a decimal, it would be 512,472.302. Lots of twos. All right, so the last thing that we have to do is we have to say, oh, but this was the total rate of change, I'm sorry, of the volume. And we have water coming in and water coming out, right? So water is leaking out at a rate of negative 6,000. So that means that water has to be coming in even faster than this number that we have. Do you guys understand what I'm saying? To kind of offset that rate out. So the rate n minus 6,000 has to equal that total change in volume. So you just add 6,000 over. So it should be 518,472.302 centimeters cubed per minute. So treat it as a total rate of change of the volume, and then at the end adjust. Okay, does that make sense? All right, one more type of problem. It's actually two, but I think I'll just do one. All right, so do you want me to go back? So shadow problems. So shadow problems are on in every single book, they're probably on every AP test. I'm sure in the multiple choice they'll have shadow problems. They're kind of weird. They're easy, but they're weird, like thinking about it. Okay. So it says Audrey is 5 feet 6 inches tall and walks at a rate of 4 feet per second away from a light that is 15 feet above the ground. Okay, so we have some kind of light post. And this light is shining down. And she's standing or walking, and she has some kind of shadow that's being formed. So when she is 10 feet from the base of the light, part A, find out what rate is the length of her shadow changing. So I'm going to make S for shadow. My students in the past have told me to do cursive S because my S's look like 5s most of the time. So we'll do cursive S. So it's saying she's walking at a rate of 4 feet per second away. That means this distance right here is changing. She is gaining 4 feet every single second. Okay, I'm going to call that X.
Fast walker.
Yes, very. She's running. Speed walking. All right, so we want to figure out how to write a proportion using this. We do have similar triangles. Do you guys see we have the height to height? What was her height? 5'6", so I'm going to write 5.5, right? 5.5 feet. So we definitely have 15 over 5.5. But then this total length, we have to write as x plus s. So we have x plus s over s. Do you guys see that in the similar triangles? Height over height equals base over base, basically. So we can multiply and simplify before we take the derivative, because we don't want to take the derivative now. It looks gross, right? So you can always rearrange and distribute and subtract. So subtract the 5.5s over. So we get 9.5s equals 5.5x. And you could even, do something with the numbers. You could like divide the 5.5 over or whatever. Yeah.
Could you use the fact that x plus s equals 10 to do anything?
Not yet. Okay, because she's walking away, so it's getting bigger. All right, so you can take the derivative at this point, which is pretty easy. It's just saying that 9.5 ds over dt equals 5.5 dx over dt, which means that these are what we call directly related. Okay, we talked about direct relations in Algebra 2. It was always y equals k times x, right? So I could divide the 9.5 over, and I'd have a rate equals some constant times the other rate, okay? So what this means is the rate that she's walking directly affects the rate that her shadow is changing, which totally makes sense. Do you guys get it? So the faster she walks away, the faster her shadow changes, okay? So basically, it doesn't matter how far she is from the base of the light. That's what throws people off. That 10, completely useless. We never have to plug that in. Okay, it doesn't matter how far she is. The thing that does matter in the real world, right, with physics, is if she's like 1 mile away from that light, is she really casting a shadow from that light? Not really, because that light is kind of dispersed, right? Does that make sense? But really, it doesn't matter how far she is. If in true, if the light was shining forever, like the sun, right? It doesn't matter. So it's kind of strange. That's what's confusing for students when they do this, because they want to put that 10 in somewhere, and you don't actually need it. So it says at what rate is the length of her shadow changing? So the length of her shadow is this ds over dt. So 9.5 ds over dt equals 5.5 times 4. She's walking away at a rate of 4 feet per second. So when I divide it out, I get ds over dt equals 2.316 feet per second. So that's part A. Now part B is very simple. It's phrased a little bit differently though, and this is what's a little bit confusing, because for part A it says at what rate is the length of her shadow changing. Do you guys see on the ground, that's the length of her shadow. That's the S, right? But at what rate is the tip of her shadow moving? The tip of her shadow is a little bit different. The tip of her shadow involves how fast she's walking and how fast the shadow is changing. Do you guys see? The tip of her shadow is actually the x plus s, because it's that distance right there. How fast is that point moving? Do you guys see what I'm saying? Okay. So the tip of her shadow is going to be dx over dt plus ds over dt. Right? So maybe I should say tip equals x plus s. So when you take the derivative, the rate of change of the tip of the shadow, it equals that. So dx over dt was the 4, and then 2.316 was what we found. So we get 6.316 feet per second. Okay, so her shadow is changing in size, but she's also walking or running or whatever. So that's moving the tip of the shadow as well. Yes, do you get it? It's kind of weird. That's what people don't like about these. All right, and the last type of question we have involves some trig again. So it says a sandbag is dropped from a balloon at a height of 60 meters when the angle of elevation to the sun is 30 degrees. Find the rate at which the shadow of the sandbag is traveling along the ground when the sandbag is at a height of 35 meters. Okay, so I don't know if you guys have, if you guys can visualize this or not. I need like a video of this. So as this drops, okay, its shadow is right here to begin with. Yeah.
Please don't take umbrage to my remarks, but this may be the single least applicable problem I've ever encountered in all my
Why?
years of teaching that course.
Okay, you guys, have you guys ever seen this as you drop something, the shadow moves along the ground? Do you not understand what I'm saying?
I
It's
know
fine.
that a lot of people say I'll never use this in real life, but they have to. But this seems a tad.
I don't know. It's a related rates problem.
Perhaps inconsequential.
All right, here we go. So find the rate at which the shadow is traveling along the ground when the sandbag is at a height of 35 meters. So what's going to happen is as the sandbag drops, the shadow is going to zoom over here, and it's going to end up being directly below it. Does that make sense? Do you guys understand that?
Wait, is it directly below when it's on the ground?
As it's falling, yeah, as it's falling, it's going to go to directly below it. Yeah. So how do we do this? Okay, the rate that the sandbag is dropping, I gave that to you. So I gave you the position. So the position of the sandbag is this. That's, you know, the original height minus gravity. Gravity times t squared. Okay, so as we set this up, right, that's going to be its position. We'll call that y. Or I guess I called it s in the problem, so we'll call it s. All right, we have our 30 degrees. And our shadow's path is also changing. We'll call that x. But our 30 degrees never changes, right? It just is becoming a smaller triangle, and so on. Okay, so our 30 degrees is constant. So we're going to have opposite over adjacent. So we're going to say tangent of 30 equals opposite over adjacent. But that s ends up involving the 60 minus 4.9 t squared. That's what it is. So I'm going to have tangent of 30 times x, and then times all that. And now I can take the derivative. But the nice thing about this is when I take the derivative of a t, it's dt over dt. So I'm not going to need that there, right? Does that make sense? So as I take the derivative, I'm going to have tangent of 30, which is a number, times dx over dt equals negative 9.8t, and then dt over dt is just what it is. It's 1, right? And we can solve it out. So we want to know when the height is 35 meters. Well, we can find out 35 equals 60 minus 4.9 t squared. We can solve for t and then plug that in here. And then the dx over dt is what we're solving. So we get our t, we plug it in here, and then we finish it out. Okay. So I think we're running out of time. Let me pass out a couple things to you guys.